We're talking about molecular orbital theory for the main group elements in the second period. That's boron through neon, seeing if they could make diatomic molecular species. And so things are going to get a little bit more complicated than what we've seen before, in that we're now going to, besides having just sigma orbitals, we're going to have pi orbitals, both bonding and antibonding. So boron, 1s2, 2s2, 2p1. It's in group 3. And so we've got 3 valence electrons. The inner core 1s2 electrons don't participate in the bonding. So we've got 2 borons coming in, each with 3 electrons. So that means we have 6 in all. So they go into the lowest available energies levels. So 2 go in the 2s. 2 go pair up and go in the 2s star. And then we have 1 electron each going into the pi 2py and pi 2pz orbitals. And so if we look at the bond order, and bond order, if you remember, is 1/2 the number of bonding electrons minus the number of antibonding electrons. And so we've got 2, 4 bonding electrons minus 2 antibonding electrons. So 4 minus 2 is 2, and half of 2 is 1. So the bond order for B2 is simply B1. And the electrons are unpaired, so this guy is paramagnetic, this species. Let's look at C2. Carbon's in group 4 because it's got 4 valence electrons. That 2s2, 2p2. We've got 2 of them, each bringing in 4 valence electrons. That's a total of 8 valence electrons. They go into the lowest available energy levels. So 2 in the sigma 2s, 2 in the sigma star 2s. Now we have 4 electrons to put in the pi 2py 2pz. So first they go in unpaired, and then they pair up. And so visually you can see how the sigma 2s electrons, sigma 2s and sigma 2s star electrons cancel one another out. We've got 4 bonding electrons. So 1/2 of 4 would be 2. So the bond order for C2 would be 2. Or if we do the total number, you can add in the 2s and the 2s star. That would be 6 bonding electrons minus 2 antibonding electrons. 6 minus 2 is 4. Half of 4 is 2. And so now all the electrons are paired. It's diamagnetic, just what we see in nature. N2, group 5. 2s2, 2b3 for each of the nitrogens. Each have 5 electrons. There are 2 of them, so now we have 10 electrons in all to put in. They go in the lowest available energy, and Hund's rule needs to be applied. If we have degenerate orbitals, they remain unpaired. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So once again, visually, we can see how the 2s and 2s star cancel one another out. We've now got 6 bonding electrons. 1/2 of 6 is 3, so the bond order is 3, and this is diamagnetic. And we've actually seen stable species truly in nature with nitrogen. And so if you remember, When we do the Lewis structure for those, that's what the Lewis structure for N2 looks like. So as the bond order increases, we see that the bond length decreases, gets shorter, 159 to 131 to 110 picometers, and makes the bonds harder to break. The bond energies increase from 287 to 627 to 941. As we look at the remaining three elements in this second period, you're going to see that at the very top of the chart, energy chart, that our pi star and sigma star orbitals, they flip-flop. And that the pi star orbitals are of lower energy than the sigma star orbitals. And that results due to the interactions of the p orbitals and s orbitals for the lower ones versus it not happening for the these larger molecules. And so that because of the lack of interaction, they flip. So oxygen is in group 6, 2s2, 2p4, 6 valence electrons. 6 times 2 is 12. So let's put them in our boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And now we go to pi star, 11, 12. And they're unpaired. It's paramagnetic. And that's the beauty of molecular orbital theory, is predicts correctly whether the molecules are para or diamagnetic. And molecular oxygen is paramagnetic. So the bond order, we've got 2, and 2 is 4, and 4 more is 8 electrons in that are bonding electrons and bonding orbitals, and we've got 2, 4 total that are in antibonding. So 8 minus 4 is 4, a half of 4 is 2. We got a bond order of 2. If you remember the Lewis diagram for molecular oxygen, it shows a double bond order of 2. F2, fluorine is a halogen. It's group 7. Means you got 7 valence electrons. 2s2, 2p5. And so now we've got 7 times 2 is 14 electrons to put into our energy diagram. The first 2 go into the sigma 2s, 3, 4 in the sigma star 2s, 5, 6 into the sigma 2px. So we put in 2, 4, 6. We got to get up to 14. So watch these as they go in. They'll go in unpaired first, according to Hund's rule, and then they'll pair up. So we put in 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14. If we do the bond order, we've got 2, 4, 6, 8 bonding electrons, 2, 4, 6 total antibondings. So 8 minus 6 is 2, a half of 2 is 1. We got a bond order of 1. And fluorine is certainly found in nature as a diatomic molecule with a single bond. And it's diamagnetic. Lastly, we can look at neon, group 8. Eight valence electrons. So we've got 16 electrons to go in. And so we're going to wind up filling up all these orbitals. 2 in the sigma 2s, 2 in the sigma star 2s, 2 in the sigma 2px. Put 2 in the pi 2py 2pz, unpaired. Then we pair them up. Then we go to the antibonding pi 2py 2bz. Unpaired, now paired. So now we got 14 electrons, and now we go to 16. And we've filled up all the boxes. We've filled up all the molecular orbitals. The number of bonding electrons equals the number of antibonding electrons. And so we've got a bond order of 0. And diatomic molecular neon does not exist. So it's a game, filling electron game, similar to what we did to atomic orbitals, except now we're putting them in to molecular orbitals. We've been able to determine the bond energy. We saw that with multiple bonds, that triple and double bonds are shorter than single bonds, and that continued to be the case with oxygen and fluorine. Oxygen is a little bit longer double bond length than the nitrogen triple bond. Then fluorine has a long bond length because it's only a single bond, and those bond energies correlate. And that the shorter the bond, the higher the bond energy. The longer the bond, the lower the bond energy, the easier it is to break. And so that's our discussion about molecular orbital theory for the second period for the P block. Thanks for listening.